This is lecture 16, and today is the third discussion session on phase noise and jitter. So let me do a quick recap of what our final aim is. So we have some signal V out of T. This is a clock signal given by A cos of omega naught T plus phi n of T. So this phi n of T, I can calculate its power spectral density and then I get S phi of F. This phi n of T sampled and scaled, what does that give? Absolute jitter AK. So this is after I sample and scale phi n of T, right? And once I have AK, I can calculate its power spectral density. So now AK is a discrete sequence. Therefore, this will be of the form SA of e power j omega d, where omega d is the discrete frequency. Now, I can also take the power spectral density of V out. This will give me a voltage spectral density, a power spectral density for the voltage quantity SV of F. We already saw the relationship between S phi of F and SA of e power j omega d. And given S phi of F, we now know how to calculate the power in the sequence AK. And once you calculate the power, you can also calculate the sigma. Now, in this class, we are going to focus on the relationship between S phi of F, which is the PSD of phi n of T, and the PSD of the voltage signal. This is okay? Now, before I move on with this relationship, do you think it is important for us to know what S phi of F is, or is it just enough if I can calculate AK? Is there any application that you can think of where S phi of F itself is more relevant than the jitter values? You understood the question? Correct. Correct. So is there any application where the power distribution is more relevant, or is it enough if I can calculate sigma A square? So jitter, RMS jitter, the power in jitter. So these are also quantities that can be calculated. Would I be interested directly in S phi of F for any application?
So if our necessary this quantity is for large,
right. Yes, that is a very good example. So let me elaborate on that. So let me take a very basic receiver architecture. So you have an antenna followed by an LNA. Then this goes to a mixer where we multiply it with, let's say, cos omega naught T. And then this goes through a low pass filter, finally to an ADC. Right. So let's say the signal here is at FC, some carrier frequency. So if I were to look at the spectrum of this will be somewhere around FC and minus FC. Right. Now, so then I have to multiply it with a frequency FC. So this is cos of omega c into T, and its spectrum would look like this. We will have two impulses at FC and minus FC. Now, when I multiply both, the spectrum at this point would simply be these bands shifted to DC, right? So you'll get something around DC. Now, instead of having an ideal clock, we have a jittery clock. So you have cos of omega ct plus phi n of t, which means now instead of having impulses at FC and minus FC, you would see that the power has now been spread around FC and minus FC. Correct. So now you see that if you convolve this, you don't exactly get the information that you want at DC, right? It will not appear exactly at DC. A very nice way to think about this is, what if the information we want was already an impulse, right? Ideally, we would have liked to see the same impulse at DC. Now, instead of that, you will see the phase noise of the oscillator scaled and appearing at DC. So this is indeed a problem. In fact, this problem gets worse if there was another blocker very close to FC. Now this blocker will get multiplied by the corresponding frequency component of the phase noise, and that can also fold back into the baseband. So the phase noise spectrum of the clock used in the mixer, so this usually comes from a local oscillator. So the phase noise of this local oscillator clock is a very relevant parameter when you are designing RF transceivers. Okay. Now, another example I can quickly give you is, for example, even in the case of the delay lock loop, we now know what the relationship, the transfer function from input to the output is. Correct? It is supposed to be all pass, but you can have peaking. Right? So now, if I know what is the shape of S phi of f, we can calculate how much, what kind of PSD is appearing at the output. So you multiply S phi of f with the square of the transfer function from input to output. So this way, knowing the shape of S phi of f allows us to calculate the spectrum of the output noise. Okay. So now we are going to look at the relationship between SV of f, which is the voltage domain signal, and S phi of f. So let's take the signal once more. So this is some amplitude into cos of omega naught t plus phi n of t. Let me expand this. What do I get? Expand the cos of a plus b. Cos omega naught t into cos phi n of t minus a into sin omega naught t into sin phi n of t. Okay. So now we are going to make a reasonable assumption. We are going to say that phi n of t is much, much smaller than 1. Okay. Now this is called as narrowband FM approximation. So once I make this approximation, what change can I make in this equation? This is equal to 1, then phi n of t. This is clear? So then this becomes a cos of omega naught t minus a sin of omega naught t into phi n of t. Okay, so now let us look at the voltage. Let's look at the PSD of these two. Right? So this one is very straightforward. So at f0 and at minus f0, you would have a square by 4 and a square by 4. Okay. Let's say phi n of t has some S phi of f, and it is given by a function like this. Okay, sorry. So this is around DC. And let's say this is the shape of S phi of f. Now a sin omega naught t is again around f0 and minus f0. You have a square by 4 and a square by 4. Okay, so far okay? Now, these two quantities are multiplied in time domain. So they have to be convolved in frequency domain. What do I get if I convolve them? So you will have this S phi of f scaled by a square by 4 and translated to f naught and at minus f naught, right? So if this is 0, at f naught, you will get S phi of f into a square by 4. At minus f naught, you will have a square by 4 into S phi of f. Is this clear? Okay. So now, can you tell me what would be the PSD of V out of t would be? So you know the PSD of a cos omega naught of t. You know the PSD of this. So I want the PSD of V out of t. That is our final aim, right? So it will simply be the sum of these two plots, right? So my SV of f is going to be, so I will have around f naught, I will first have an impulse of value a square by 4. Then I also have the skirt whose value is a square by 4 into S phi of f. So similarly, at minus f naught, I have this impulse at a square by 4 and the skirt a square by 4 into S phi of f. This is fine. So the change, if I'm looking at only the PSD, the subtraction doesn't come into picture. If you were looking at the Fourier transform and then magnitude and phase, the subtraction will come in phase. The two signals are now uncorrelated because of phi n of t. Therefore, they add in power. Okay. So this is the two-sided SV of f. Now I can calculate the one-sided SV of f. How would that look like? So at f naught, I will have the impulse of a square by 2. So I shouldn't mark the arrow here. Right? And I'll have the skirt of value S phi of f into a square by 2. This is okay. Let me also plot my S phi of f to the side. So around 0, this is S phi of f. Okay. So S phi of f, I have plotted the two-sided S phi of f. So now looking at both of these, can you tell me the relationship between SV of f and S phi of f? So S phi of f scaled by the carrier power is appearing around f naught. Correct? Or in other words, if I have the skirt around f naught, I can take that, scale it down, normalize it to the carrier power, and then shift it to DC, I get S phi of f. Okay. So now generally, when you report phase noise as such, you report it in terms of its frequency domain values, right? So you ideally want to report S phi of f. And in the most layman's terms, what you do is you simply say the value of S phi of f is so much at a given frequency. This is what you say. But clearly, the statement I made is very vague. Because what do you mean by value at a particular f when you are looking at power density, right? I have to talk about a small band of frequencies. So the official definition is done in the following way. The first step is to identify an offset frequency. So you decide on an offset frequency, let's say some delta f, okay? And all this definition is now based on the one-sided SV of f, the voltage domain PSD. So I decide on a delta f. It's called as offset because it is going to give us a frequency f naught plus delta f. So here is my delta f, and this frequency is now f naught plus delta f, correct? Let me also mark that here. This is my delta f, okay? Now I look at the 1 Hertz bandwidth around my delta f, and I calculate the power there. So I'm looking at a 1 Hertz bandwidth here, and I'm calculating the power in this. Okay, so that is the second step. So calculate the power in 1 Hertz bandwidth at f is equal to f naught plus delta f for SV of f. Okay. Third step is to, what should be the third step? So we calculated the power here, then. So we normalize it to the carrier power. Yes, we are finding S phi of f from at a offset frequency, but this is how we formally define it and formally report it. We do that. Yeah. So using this voltage domain PSD, we are going to report the values of S phi of f.
And that you're looking at that carrier signal also is
correct. The carrier signal is present. So you're asking about the impulse, right?
Yes. So when you said what is the relationship between SV of that?
Without the impulse. Without the impulse.
SV of
so based on this equation, right, it looks like the carrier signal is present. Right? So there are certain limitations to the approximation we made here. So I'll explain that before the end of this class, right? But for now, you have raised a very good point, because if you remember, when we first discussed, if an oscillator is oscillating exactly at f naught, we expect to see an impulse, right? But if it is oscillating, if it has a jittery clock, if it was a jittery clock with its oscillation frequency instantaneously varying around f naught, we expect the energy, the power to be spread out, right? We don't expect to see an impulse. So this presence of the impulse here is against our intuition, correct? But this is what has come out of the equation. So that has happened because of some limitations in that narrowband FM approximation. Okay, but humor me for now. Let us go through this, then we'll come back to the presence of the impulse. Okay, so we normalize this power to the carrier power. And then you take the 10 log 10 of that quantity, the normalized quantity. Okay. And this will then be represented in units of dBc per hertz. dB because you have taken log 10, C because it has been normalized to carrier power, and per hertz because you are looking at the power in a 1 hertz bandwidth. Okay, and this is represented using L of delta F. Okay, so L of delta F is 10 log 10 of a ratio where the numerator is power in 1 hertz bandwidth of S voltage domain SV of F at F is equal to F naught plus delta F, right, divided by carrier power. Okay. This is also same as 10 log 10 of S phi of f, where this S phi of f is now the two-sided PSD. Okay. And when we report L of f, we generally report it for positive values of offset frequency. And this is fine because the S phi of f is symmetric around 0. Okay. So take a minute and see if you have any confusions here. So to give you an example, so if you're working with a 900 megahertz GSM transmitter, when you report the specifications of the clock, the delta F, the offset frequency you are interested in, is 25 megahertz. And the phase noise at this offset frequency should be minus 145 dBc per hertz. So it should either be at minus 145 dBc per hertz, or it should be a lower value, right? So now a very simple question. We have done detailed calculations with, it's not recording. We have done detailed calculations of S phi of f now. Can you tell me the unit of S phi of f? Is PSD. So what is the unit? So let's also look at SV of f. What is the unit of SV of f? This is V square per hertz. So what should be the unit of S phi of f? This is not a voltage quantity, right? So if I have a voltage quantity and I take the PSD, it becomes V square per hertz. So I had a phase quantity. I take the PSD. What should it be? Radian square per hertz. So this is okay. So then let me confuse you a little bit more. PSD is power. The definition of power is simply expectation of x of t the whole square, right? Now I can talk about the power or energy in any signal. It could be current, voltage, phase. It need not be voltage specifically. Any signal, if you square it and take the expectation, you should get the power, right? Yeah. So now here is another question I have. Here we saw that if I take S phi of f and I multiply it with a square by 2, it is now a voltage domain PSD. Is that consistent? Let me give you a better example for this problem. Let us look at this equation, right? So calculate the unit, determine the unit of these three quantities and tell me if this is consistent. This is voltage. This is also voltage. This is voltage into radian. Are you convinced? So do we have a problem, or is this, I mean, how do we be okay with this sort of an inconsistency? Problem in the approximation, but if it is dimensionally wrong, then we shouldn't be working with an equation that is dimensionally wrong, right? So what is the dimension of phi? Units is radians, I agree. What is the dimension? So do you remember how radians was defined in the first place? So let's say you had an arc, right, which is part of a circle. And let's say this arc length is some L. And let's say this is the radius of that circle, of which this arc is part of. right? Then an angle in radians is defined as L by R. So radians as such is, so this is theta. So theta in radians is defined as L by R, right? Which means radians is dimensionless. Okay. Therefore, this equation, unit-wise, we have some difficulty in reconciling, but dimensionally, this equation is correct. Right. So if you ask me what is the dimension of S phi of F, I would simply say 1 by hertz. Okay, so there is no dimensional inconsistency. Okay, so now I want to introduce you to another circuit called as voltage controlled oscillator. So we will do some phase noise related calculation based on this particular circuit. In short, this is VCO. So you are aware of a voltage controlled delay line, right? So this basically consisted of a delay line. If I give an input, I will get the output with some delay TD. And this delay TD can be controlled by varying a control node voltage VC, right? And I can derive an expression such as TD is equal to T0 plus KDL into VC, where KDL is expressed in what is the unit? If I write it in terms of T0, second per volt, right? Now, if I take, let's say, a series of inverters, right, and I make them tunable with respect to VC, this becomes a VCDL. Now, the moment I connect it like this, it becomes, and I take odd number of tunable inverters. Now, this is an oscillator. It is going to give me an output frequency, and I can control that oscillation frequency by changing VC, right? So this is one of the ways in which we implement VCO. But for now, all that you have to understand is that VCO is a circuit that is going to give me an output frequency omega out. And this output frequency is now a function of VC, right? There is no input. We just have the only input is VC, the control node voltage, and it is giving me an omega out. And I can write the expression for omega out as some omega naught plus a gain KVCO into VC. What should be the unit of KVCO? Radian per volt. Everybody agrees? Okay. What is the unit of omega out? This is radian per second. Now what should be the unit of KVCO? It should be radian per second per volt. Okay. Now, if you had missed out the per second, it is now dimensionally inconsistent. That is a problem. Okay, so now this is omega out. So if I were to look at the voltage domain signal, how would that look like? So this will be V out into, say, some amplitude into cos of the total phase of the signal, right? It's cos of total phase. So how can I calculate total phase in terms of omega out? So I want to look at, so if I put a oscilloscope probe at this node, what would I see? Basically, how does a voltage domain signal look like? Right? So I know that if I know what is the total phase of the signal, I can write it as a cos of total phase. Assume that it is a cosine wave, right? What I have is an expression for omega out. What is the relationship between total phase of the signal and the frequency of that signal? Is it only omega out into T? Do you remember the official definition? So when you were working with this total phase with respect to t, how did you calculate the omega? You took the derivative, right? So the relationship between that of total phase and omega out is either a derivative or an integral relationship, if I'm looking at the opposite relationship, right? So this is given by integral of omega out into dt. Sorry, integral of phi out into dt. Which is equal to, so a cos of, this will be equal to omega naught into t plus kvco into, now it depends on whether vc of t is a constant or not, right? So the generic expression would be vc as a function of t dt. This is okay? Now, if vc is a constant vc naught, then v out will become equal to a cos of omega naught t plus kvco into vc naught. Okay, so an easy way to think is to imagine the relationship as a graph, right? So this is vc, this is my omega out. When vc equal to 0, it is omega naught. And then the slope of this line is kvco. So now if your vc is time varying, which means that your omega, you're basically moving around this curve. So your omega out is also time varying. Okay. Sorry. A cos integral, correct, sorry. Yeah, right. Is this okay? Okay, then let me give you a small question we can work on. Assume that Vc of t is equal to Vm cos of omega m into t, where Vc of t is the VCO control node voltage. Okay, so first part of the question is to find V out of t. So you can assume that V out of t is in this format, a cos of phi out of t. It is a frequency modulated signal, but what is the exact expression? So V out of t will be equal to a cos of omega naught t plus, this is basically integral of kvco into vc of t, where vc of t is now vm into cos of omega m t dt. So I can take kvco and vm outside the integral because they are constants. And what is integral of cos omega m t dt? That will give you sine omega m t by omega m. Okay. So next part of the question is to calculate the peak-to-peak jitter. In V out of t. Give it a try. Okay, so our signal is now A cos of some total phase. When do you have the zero crossings for this? So let me write the total phase. Phi out of t is now omega naught t plus KVCO Vm by omega m into sine omega m of t. So by default, what value should phi out of t take for us to have a zero crossing? So it has to be in the form of 2 pi k plus pi by 2, right? Then you will get zero crossings. So now in the absence of this whole term, in the absence of this extra term, these zero crossings would have happened for some value of t. Now that value of t has shifted because of this, right? So in effect, this is going to be my operating point. And this is the additional small signal phase, right? Riding that operating point. So this is sometimes called as excess phase. If this was totally random and if we knew that it was phase noise, we could have called it as phi n directly, right? Now, you'll see that in certain cases, you would try and modulate this VC to get a required modulation at the output. So let's stick with the term phi x excess phase for this calculation, right? So now what is the peak value of excess phase? When do you get the peak value? When sin omega t is 1, either plus 1 or minus 1, depends on maximum or minimum you're looking. So that is KVCO Vm by omega m. So what is the peak to peak value? Twice of this, right? So this is the result that you mentioned. Now, how do I convert this to jitter? How do I convert phase to something in time domain? T naught divided by 2 pi or divide by omega naught, right? So this is KVCO Vm by omega m omega naught. This is okay. And the jitter that we are dealing with now is very deterministic. Often abbreviated as DJ. Okay. So now last part of this question. Can you calculate the Fourier transform of V out of t? So calculate the magnitude of the Fourier transform. You can use the narrowband FM approximation. So KVCO Vm by omega m is much lesser than 1 radians. So my suggestion here would be to manipulate this V out of t first and see if you can represent it as only cosines or individual cosines or sines. Then it becomes easier to place the impulses in the frequency domain. Beta by 2. So once you calculate the sideband magnitude with respect to the carrier magnitude, you get beta by 2, for which the full expression is KVCO Vm by twice omega m. Okay, so let's do some sanity checks on this. So first, is it dimensionally consistent? What is the dimension of LHS? Dimensionless. What about RHS? Dimensionless. Why? Because this is in volt, KVCO is in radian per second per volt, and then you have radians per second here. So this is also dimension. Dimension-wise, it is fine. Now, does this make sense intuitively? Now, no, dimensionless part is fine. I was asking if this expression makes sense to you, intuition. Is there some intuition or it's just some expression sort of? Like what happens if your KVC or VM goes to 0? Right? So what happens in this plot? So only the carrier impulse will remain on this plot, right? So that way, this equation sort of makes some sense, right? So you will not be able to detect if you have missed a factor of 2 or some factor of half, etc. But at least it is not very way off from the results that you expect. Okay. So now let me give you another very interesting problem. So let's say I take this VCO. I connect a resistor at its input. Now this resistor will have thermal noise. So let me model that. And I have a resistor of value R. Can you calculate what S out of F should be? So you have to calculate, let me be a little bit more specific. What is S phi of F? And how would S V of F look like? So let me help you with this. So we have to now calculate how the phase at the output is going to appear when there is some voltage noise at the input. Right? So the first step would be to find out what is the transfer function from this point to this point. Once we have the transfer function, we can multiply the PSD of Vn square, PSD of this thermal noise, with the square of the magnitude of transfer function. Right? So let us try and figure out what this transfer function is. So omega out is given by omega naught plus KVCO into VC. We are interested in phi out, right? So what is the expression for phi out? Integral omega out dt, right? Phi out of t will be integral from 0 to t, omega out of dt. That is omega naught into t plus KVCO into VC of t dt. This is okay. Now, like I mentioned before, this is acting as our operating point, and this is the excess phase, right? So we are basically interested in calculating the relationship of how excess phase relates to VC of t, right? So excess phase, the time domain expression is KVCO 0 to t, VC of t dt. What is the transfer function? So I have to do phi x of s will be equal to KVCO divided by s into VC of s. So now I have this transfer function given by KVCO by s. Okay. Now, what is the spectrum of Vn square? It's a resistor. 4 kTr is one-sided. So let me write 2 kTr because we'll deal with two-sided now. It gives us better intuitions. Right? Let's look at the two-sided spectrum. So around 0, this Vn square F will have the value 2 kTr. Okay. So now what is S phi of F? This will be equal to modulus of h of 2 pi f, h of f the whole square into Vn square f. What is mod h of f the whole square? KVCO square by omega square. Convert that into F to be equal to 2 pi F the whole square. So this into Vn square of F is 2 kTr. So this is equal to KVCO square by 2 pi square kTr into 1 by F square. This is okay. So how does S phi of F now look like? So around 0, I will have a 1 by F square spectrum, right? So that will now look like this. Is this okay? Right? Now S out of F, voltage domain. So SV out of F, SV of F. How would this look like? Let me draw the one-sided PSD. So around the required frequency, some F0, I will have an impulse based on the narrowband approximation. I will have this impulse corresponding to the frequency F0, and I'll have S phi of F scale and shift. This is okay. Again, this figure you have here is also not in line with the intuition we have, right? Because after all, this is simply an oscillator, right? The oscillator is oscillating, just that we know its F0 is now going to vary around few values around F0, right? On an average, it is still an oscillator. But it looks like, one, we have an impulse at F0, and two, this phase noise is increasing, correct? The power around F0 is also very, very high. Okay. So that doesn't make intuitive sense, right? So now let me show you the two issues that we are dealing with. So S phi of F, we said, should be this, right? Then if we were looking at SV of F, this is with the narrowband approximation. We are getting the result that there should be an impulse at F0. So this is at 0, impulse at F0, and S phi of F is scaled and shifted, right? But our intuition, this is the intuition for SV of F, was that we should see something like this. Instead of impulse, the energy, the power now has to spread out around F0. Now it turns out this narrowband approximation does give you errors as you approach closer to F0. In practice, if you were to calculate this PSD exactly, that is, you take the time domain waveform, find out its autocorrelation, then take the Fourier transform, what you get is something called as a Lorentzian spectrum. And that Lorentzian spectrum has a shape like this. Okay. So in the Lorentzian spectrum, you wouldn't see an impulse at F0. So this is a voltage domain signal. You wouldn't see an impulse at F0. And it's the 1 by F square shaping doesn't happen very close to F0. It goes to some finite value. Okay. Now it turns out narrowband approximation is valid for frequencies above few hundreds of hertz. For offset frequency, above few hundreds of hertz. So if you are looking at some delta F, and this delta F is around 1 kilohertz or so, then you can easily compare the result you get here with this result. It becomes invalid as you move closer to F0. That is when the delta F becomes closer to 0. Okay, so as a mathematical tool, this narrowband approximation is still very useful. It gives you very intuitive results. It directly comes from the math. And for offset frequencies greater than few hundreds of hertz, you can easily use it. Okay. Okay, I think we can end the class. If you have any questions, you may ask.